magnetic induction. We are going to have a look at the parameters and calculations. This phenomenon is defined by LENZ'S law, which reads as follows. An induced electromotive force, EMF, always gives rise to a current whose magnetic field opposes the change in original magnetic flux. The direction of the current in the coil induces a magnetic field which causes a current that wants to flow in the opposite direction as the original current. Remember the iron filings experiment? The direction of the induced magnetic field is indicated by the right-hand rule. What happens if you pass a magnet through a conductor twisted in a coil? Magnet movement through a coil equals EMF. As you can see, the movement of the magnet left or right also changes the direction of the induced current. So does the change of the magnet's polarity, which is called self-induction. Concept of self-induction. When the battery is connected, a conventional current flows through the coil, causing a magnetic field to be generated with a concurring EMF produced. At the moment the current starts to flow, this EMF produced through the generated magnetic field will cause an opposing current to be generated. We call that self-induction. This current works against the original current, also called reverse current, causing momentarily an apparent resistance to the flow of the original current, called reactive inductive resistance, XL, measured in ohms. Concept of self-induction. When the original current eventually overcomes the resistive action, there is no more change in the current, and the induced current will cease. The original current will then be at maximum value. When the battery is disconnected, the original current will fall away, decreasing momentarily through the link provided and indicated by the red positive sign, causing another current to be generated by an opposite induced EMF. This time the current is now in the same direction as the original current. If the positive sign is now a lamp, then the circuit is now of course connected to that lamp. The bigger current will now temporarily light up the lamp. This EMF and current is also called back EMF or complementing current. As soon as the EMF is expended through the lamp, the current will also disappear, and therefore the self-induction cycle will also have disappeared. Remember Fleming's left-hand rule? Moving a conductor through a magnetic field induces a current as indicated by this rule. Try it. Just a quick summary. Current through a conductor induces a magnetic field. Movement of a conductor through a magnetic field causes a current. An opposite EMF is generated if there is change in polarity, whether it is the current or the magnetic field. Let's have a look at Faraday's law. Faraday's law tells us the magnitude of the EMF produced. On the other hand, LENZ'S law tells us the direction that the current will flow. Faraday's law of electromagnetic induction actually consists of two laws. The first law describes the induction of the EMF in a conductor. The second law quantifies the EMF produced in the conductor. Transformer action, one of the most important electrical phenomenon. Based on LENZ'S law and Faraday's law, a current flowing through a coil will always generate a magnetic field, measured in henries, in a ferrous metal bar running through the coil. We call it an electromagnet. Mutual induction. This usually happens between two coils in close proximity. If two coils are placed near each other in the same plane, a changing current in one coil will induce an EMF in the other coil. From Faraday's law, the EMF induced in coil 2 is proportional to the rate of change of the magnetic flux passing through it. The Henry, using the symbol H. Two circuits have a mutual inductance of 1 Henry. If the EMF induced in the secondary circuit is 1 volt when the current in the primary circuit changes at a rate of 1 ampere per second. Based on these principles, if we want two coils on the opposite sides of a closed iron core, which are relatively in close proximity, it is called mutual inductance. We then created a practical application for these two laws, which we call the transformer. Although there is no physical contact between the two coils, the secondary side, that's on the right hand side, will receive a current from the primary side through the process of induction. Can we now determine the values of the induced outputs? The input side of the first coil is the primary winding. The output side of the second coil is the secondary winding. The same is applicable for input and output voltages and currents. The following are the formulas for doing this. The ratio between the number of turns N, volts V, and I is as follows. N1 over N2 equals V1 over V2, but I has a inverted ratio, where I2 over I1 makes up the last ratio. Why does the current show the inverse ratio to the other two parameters? Find out this answer because it might just be asked in the test. Now let us do the following exercise. A single phase transformer has 1000 turns on the primary winding, which is connected to a 230 volt AC supply. The voltage and current on the secondary side is 20,4 volts and 4,3 amperes respectively. Draw the circuit and determine the following. The turns ratio for the secondary coil. What will the primary current be? Determine the turns ratio and voltage per turn. The last two questions will take a little bit more skill. Here are the answers. The number of turns is 87. The current is 381 milliamperes. The turns ratio is 11,5 and the volts per turn is 0,23 volts. This is the end of study unit 4. You will receive an online test on the last two study units, namely 3 and 4, very soon.